Okay, so let me share my screen. Is it visible now?
Yes, sir.
Okay. We were discussing pipelining, and this will be our last class in this semester. Just few topics are left, and we'll discuss that. I remember that we were talking about different kinds of hazards. We discussed structural hazards, control hazard, and yesterday we started discussing data hazard. We have already discussed. Last time we were discussing control hazard. We will finish the remaining portion today. And then we'll discuss some general issues, then how the hazards can be detected, how the stall can be enabled, and discuss some hardware issues. Well, so control hazard, as you know, that this arises when you have a branch instruction, and once the branch instruction enters the pipeline, after one clock cycle, the next instruction also enters into the pipeline. However, there is no guarantee that whether or not the instruction which follows it sequentially would be executed. If the branch is not taken, then it will be executed. Otherwise, the instruction which lies at the target address would be executed. So therefore, there may be a need for flashing out the next instruction if it is already entered, which causes hazard. So this is what is called control hazard. Sorry. So this arises when the computation for the destination of the branch, at the same time the PC update operation that is still awaited. So you are not sure whether the next instruction will be executed or whether the target instruction will be executed. In other words, the instruction that would be executed next is still uncertain at this moment. So as you see in this example that, so you have branch T1, T2 target. So if the branch is taken, the instruction at the bottom with label target would be executed. Otherwise, the sequential instruction at PC plus 4 load that would be executed. Okay. Now, in general, as we have seen yesterday, that control hazards are expensive, because the PC update is done in the memory stage. And so therefore, you have to wait at least 3 clock for 3 clock pulses in order to, when the outcome of the branch is known. So therefore, just to recall that what you have studied yesterday. So as you see that, so there are these 5 stages, and the branch is being updated here. See, branch is computed here, whether the difference of these two registers is 0. And if it is 0, then this, if the difference is 0, then the 0 line would be set to logic 1. And this AND gate would be enabled, and this signal tells you whether this is a branch instruction, and therefore the second input of the mux is enabled, and the target address is updated here. Okay. So the memory update is taking place at the memory, the PC update is taking place during the memory access stage, MEM stage. And the computation of 0, the comparison part is being performed in the execute stage, right? This is the hardware, as we can see, which is responsible for PC update when the branch is taken. So as a result of this, as we have seen yesterday, that as soon as this branch instruction is now currently executed, and as soon as the next instruction enters the pipeline, you are not sure whether or not this will be executed, because the result of the comparison would be known here, and you are in the backward side. So then you have to insert some delays, you know. Now, since the memory update is being done, the PC update is being done here, you need to wait for at least 3 clock cycles. After that, you are sure whether or not the next instruction will be executed or the target will be executed. Isn't so? So this is the straightforward or naive technique for fixing a control hazard, that you need to insert 3 stalls. You need to wait for 3 clock cycles. After that, you would be able to ascertain whether or not the branch is taken or not taken. The other possibility is you let the next instruction to enter into the pipeline, and when the outcome is known, then if your action is, if it is correct, then you continue as before. Otherwise, you flush whatever instruction has entered during the 3 clock cycles. So this is one way of fixing the hazard. Either you insert stall, or you let the next instruction to enter into the pipeline, but at the end of the memory stage, when it is known, when it is finally known about the target, and if your assumption is not correct, then you flush out these instructions. So this overhead, you know, I mean, whatever you have done here is completely lost. I mean, that becomes useless. So you flush out this instruction and proceed as before. Now note this, in this diagram, the symbols are little different, but don't be worried about that. Instead of instruction fetch, it says instruction memory. This is, instead of memory stage, it says data memory. So there is a difference in this diagram. You know. Anyway, but it's the same. It reflects the same pipeline diagram. Well, so either you insert flush, either you insert stalls, or you continue and flush if the branch is taken. So these are the naive approaches. In any case, in the worst case, you may have to pay a penalty of 3 clock cycles, 3 stall cycles. Well, now is there any hardware solution you can think of just from common sense? Now, since the update is being done in the memory stage, that's why you have to wait for 3 clock cycles, right? Is there any hardware solution, possible hardware solution, so that can you compute branch target and PC update earlier in the pipeline? Then the next instruction would not have to wait for 3 clock cycles. Maybe you would wait for a little less. So if we want to do that, what kind of additional overhead I need to make, or I need to deploy? Just some kind of common sense solution, you know. In the branch instruction, you read 2 registers. So for example, B branch equal R1 R2. So you read 2 registers and then compare whether or not they are equal. When do you read the content of the register? In which stage?
The instruction decode stage.
Instruction decode, good. Instruction decode and register read. So during that time, you know the content of the register is read. Now, can you do the comparison in the same stage, you know, by doing by adding some extra hardware, you know? Because register read it takes a shorter time, you know. I mean, so therefore, during the entire clock cycle, we have some leverage. You can use an additional comparator there in the same stage, in the ID stage, in the ID and register read stage, so that it would read the content and immediately compare it. And at the same time, update also PC, the update multiplexer can also be brought there separately, So the idea is, in order to reduce the stall for the successor instruction, what I'm going to do that if the branch decision can be made earlier in the pipeline. Okay, so we add some extra hardware so that this decision can be made earlier in the pipeline. So therefore, if we can do so, it would reduce stalls for the successor instruction because we don't have to wait until the memory stage as before. You got the idea? Okay, so let us look into this diagram once again. So this is the place where this update is being done, and this is the place where the comparison is being done. Well, so we are not going to disturb this ALU because this ALU performs many other operations. It performs arithmetic operation, logical operation, and other operations as well. Just for the sake of comparing the content of two registers, we can add an additional comparator somewhere here. And at the same time, this PC update, this portion can also be brought here. So what I'm going to do is the following. So this is our original pipeline, our original hardware layout. So first of all, and as you see, currently this is the circuit. This is the hardware portion of the hardware, which is responsible for comparing the content of two registers and this PC update sort of stuff, right? So first of all, what I do that I redefine the boundary of my stage, so that this portion is included here. So now, and if I do this, then I can save one clock cycle because now PC update is being done in the execute stage. So just by redefining the boundary, I can save one clock cycle for the control hazard. And I can do even better, just move the whole thing, use a separate small ALU specifically for comparing to the content of two registers. That means essentially is the hardware for zero checker. So I have we add an additional zero checking hardware and also this PC update hardware and move this entire part, here in this stage. And so therefore, if it is a branch instruction, then the outcome would be of the branch would be known when you are at the end of this instruction decode and register fetch stage, at the end of the second stage, instead of here. So previously there was a stall of 3 clock cycles, right? So now we have advanced from the output of MEM to the output of IDRR. So therefore, we'll save 2 clock cycles. Is the idea clear to you?
Yes, sir.
Okay. So we can reduce branch penalty by moving the comparison of register or zero checking and the PC update hardware early in the pipeline. And we can do it in this IDRR stage. And since we have moved 2 stage earlier, and so therefore, look into this example. So this is one instruction, and then you have a branch instruction here. And this is 1 clock cycle, 200 picosecond. So the branch instruction enters into the pipeline, and you have subsequent instruction here. So let us wait for 1 clock cycle now. And therefore, at the end of this, the IDRR stage, that means here, you know that the outcome of this branch, whether the branch is taken or not taken, because the hardware has been already moved, you know. So that, and depending on that, if a stall is given, then we can certainly bring the next instruction, whether it would be the subsequent instruction or the target instruction. Okay, so that's why it is 400 picosecond. I mean, just normal pipeline, you have 200 picosecond, and then one stall, 400 picosecond. So just by doing this little bit of hardware modification, we save 2 clock cycles. Instead of 3 stalls, we now have only 1 stall. Got it? But in order to implement this, we need to, my hardware cost would increase a little bit because I need an additional copy of this zero checking hardware. And PC update hardware is the same, only thing that we have moved it in the IDRS stage. So this is one simple hardware solution. With a little bit of hardware overhead, you can resolve this. But so moving branch target determination from memory stage to the previous IDRS stage help resolve hazard in the successor instructions. That means whatever instructions are following the branch instruction, the stall incurred by them can be reduced. But could it create any other problem if I move the branch comparison earlier? You are going to compare the content of 2 registers, isn't it? So as far as the successor instructions are concerned, that is fine. You save 2 clock cycles. But is it possible that it would create some additional problem elsewhere? For the comparison, what you have to do, you need to read the content to 2 registers, R1, R2. And we are doing it in the IDRR stage. Is there any problem you can foresee?
Yes, if some other instruction is writing to the register, then.
Correct. So, you know, and for the successor instruction, it is good. But for the predecessor instruction, it may be not that good because see, you are comparing content of 2 registers R1 and R2. Now one of these registers, or maybe both of them, maybe the destination register of a previous instruction, which will be updated later stage, you know, in the write back stage, or at least in the after the execute stage, or maybe the memory stage if it is a load instruction. So the destination is awaited. So how can you compare then? So solving one problem, you know, gives rise to another problem. When you move the hardware in the previous stage, in earlier stage, it is good for the successor instruction, but it may not be so good for the predecessor instructions, you know, or it may not be so good for itself because the branch itself may now have to wait because the content of R1, R2, the registers which you want to compare, those values may not yet been updated. Therefore, it may pose problems to preceding instructions. You know, when a branch source register is a destination of a preceding instruction. Okay, let me give you an example. Here. So this is your branch instruction. We are comparing register 1 and register 4. And the register 1 is being updated here. We have an add instruction. 4 is also being updated here. And suppose there is another instruction here which does not interfere with this, you know, maybe an independent instruction. Is there any problem here? Do you need any stall or the branch is fine? R1 is updated. You see, register 1 is being computed here. It will be written here, but it will be computed here. Similarly, register 4 would be computed here. It will be updated here, but computation is over by when you reach the end of the execute stage. Is it okay, or do you need an install here? What do you think?
So it is okay.
It is okay because
We have the forwarding mechanism from
right.
EX to ID stage.
Good. So it is okay now. Because you have forwarding mechanism, and so you can those information, those are already available, and here you can make the comparison and know the target. So there is no problem in the as far as before this branch instruction, and there would be no problem following the branch instruction. Of course, following the branch instruction, you need to incur one stall because the next instruction will enter here, right? So you have to wait one clock cycle. After that, you can allow the next instruction to enter without any stall. Well, but suppose this, so there is an instruction in between here. Suppose this instruction is not there. Let me. So here you observe that if the comparison register, the registers where you are making a comparison, if these are the destination registers of the second proceeding, meaning that this is the first one and this is the second one or third proceeding. Okay, so the distance between them is at least 2. Then there is no problem. Can resolve using forwarding. However, if the distance is less, then for example, this one here you are comparing 1 and 2, 1 and 4. 4 is being updated here. 1 is load again. It is being updated at the end of the memory. So the value of 1 would be available at the end of the memory stage here, at the end of the 4th clock cycle, and this will be available again at the end of the execute, which is also the global 4th clock cycle. But the hardware for comparing these two registers, now it has been brought to the second stage. So that you cannot do, right? You need to shift this guy at least one clock cycle on the right, even with forwarding. So therefore this is stalled. Need one stall cycle, and if you move here, then it is okay. Got it? So therefore, if the branch instruction is close to the previous one, whose destination is the source of the branch, so then you need one stall here. So you have one stall earlier and also one stall for the successor instruction. Now here, one thing you notice that the instruction which just precedes branch is an R type and load is here. Suppose this instruction is not there. Just after load, the branch appears. So you have the load instruction, and following this, the branch appears. And one of the branch register is the destination register for this load. So now you can see what will happen. Because at the end of memory, at the end of the 4th clock cycle, this, the register 1 will be updated. And since the branch comparison is being done in the second stage, in the ID stage, that ID must be on the right hand side of this memory stage, right? So therefore, if you have originally, suppose this branch is just follows load instruction, but you need 2 stalls so that the ID stage for branch appears after this memory stage. So if this comparison register is the destination of the immediately preceding load instruction, then you need 2 stalls. even with forwarding, you know. Isn't it?
Yes, sir.
Okay. So see that this management of branch or control hazard is quite interesting, you know. So there may be problems in the preceding side or maybe problem in the successor side. Right? Okay. Now we also discussed that we do some kind of branch prediction. Say, for example, we can predict that branch is not taken and let us move ahead. In case the branch is taken, we flush, so that depending on what percentages of branches are being taken or not taken, we can have an average performance. But we don't have to worry about the stalls and so on. Now, moving this hardware to the IDRR stage is good for MIPS, but when the pipeline becomes very long, for example, the pipelines which are usually deployed for implementing floating point operations, those pipelines are pretty long, you know. So in those pipelines, it may not be possible to move the branch ahead, you know, the branch comparison hardware ahead, and you won't get much benefit out of that, you know, because of this predecessor conflict and successor conflict. So most of the time they do what kind of this technique, that branch prediction. Let us predict somehow what is going to happen next, and we want to make our prediction as good as possible. And this kind of fixed stall penalty may become unacceptable for long pipelines. You know. So prediction is a widely accepted technique, and there has been a lot of research has been done in how to predict the successor of a branch and so on. So we'll touch upon just some basic and simple techniques on how the branch can be predicted. So here the idea is you go ahead depending on the prediction, and stall is needed only if the prediction is wrong. If the prediction is correct, no stall is required. Typically, in pipelining, we assume that the branch is not taken. That is our default choice. Because in that case, you know, PC is already being updated by 4, and so this is a natural choice. However, in advanced branch prediction technique, we do something else depending on the history of the branch taken or not taken, and depending on that, we may take a decision dynamically. Typically, we assume that the predict not taken, which is the normal flow. That means the next instruction would be the sequential one, which follows it at PC plus 4. If it's so, we can just fetch instruction directly after the branch, after one clock cycle with no delay in the pipeline. And let us see what happens, you know, just like this, you know, that we considered this one. So we have a branch instruction and load instruction here. And what we do that we just normally follow in one clock cycle, delaying one, just in every clock cycle we are processing one instruction. And so if the prediction is correct, then the branch is not taken, then there is no problem. You know? I mean, we don't lose any time. If the prediction is incorrect, so then I insert one bubble, and since the hardware is already moved to the register and ID stage, so with one bubble I can decide this. So we pay. So in the previous case we have no stall. Here we pay a penalty of 1 stall with the modified hardware if the prediction is incorrect. All right. So let us now quickly summarize whatever we have studied in control hazard, and then we will discuss a little bit in more detail different techniques for prediction. So if it is a branch, if you don't do anything, then 3 stalls per branch for the following instruction. So one possible hardware solution is that move zero checking ZC and target address computation TC earlier. It needs additional hardware. It solves the successor problem, but it may pose some problems with the preceding instructions. Third possibility is no, you just predict branch not taken and go ahead. And so if it is not true, then you flush one following instruction in the presence of this additional hardware. Okay. So no stall if the branch is not taken, and squash instruction in the pipeline with one stall with early, zero checking and target address computation. Now, this is average statistics by looking, which has been observed in different kinds of programs, that 47% branches are not taken on the average. PC plus 4 is already calculated, so you can fetch the next instruction when you assume this branch is not taken. So this is the summary so far, and now we'll discuss a little bit more detail. What are the different kinds of realistic prediction techniques? Now, this can be classified into two groups. One is called the static prediction. So you predict ahead of time. And so either it may be taken or branch not taken. So what you do that if you are in a loop, and then a loop is supposed to be executed many times in most of the cases, So you predict backward branches taken, and you predict forward branches not taken. So this is a typical static approach. So your prediction may or may not be true, and if it is not true, then you pay a penalty. Of course, you need to have some kind of hardware mechanism in order to figure out whether your prediction is true or not. That means you have to wait for some time, and when the branch outcome is known, the hardware must flag that the prediction has been wrong and appropriate actions to be taken. So this is static. I mean, we don't change our prediction behavior. Backward branches always taken, forward branches always not taken. That we predict. Dynamic also, depending on the branch prediction, depending on the actual branch behavior. For example, if we are moving in a loop, we see that whether the previous branch has been taken or not taken. So if it is taken, then we predict that it would be taken next time. Now, prediction can never be 100% true. So this is a technique where hardware measures actual. There are hardware circuitry which measures or which keeps a record of the actual branch behavior in runtime. So you record the history of each branch, and depending on you decide the future prediction. So basically, if a branch is taken, if the previous branch is taken, then you predict that the future behavior will continue the trend. If the previous branch is not taken, you assume that the next branch will not be taken, something like that. So this is sort of dynamic, right? And so it depends on how many so since you're keeping a record of the history, it depends on the depth of the history as well, whether you are keeping track of the last branch or the last two branches, something like that. So one is static, to decide ahead of time. You don't decide anything in the runtime. Here, the decision is being taken in the runtime. Now, it has been observed that when the pipeline becomes long, or in superscalar pipeline. Superscalar means, the multiple instruction can be executed in parallel. You have additional hardware resources so that multiple instructions which are not data dependent can be executed in parallel. So in those high performance machine, branch penalty becomes more significant. And so therefore they wanted to make the branch prediction as accurate as possible. And typically this dynamic prediction technique, which we discussed just now, that depending on the runtime behavior, that is adopted. So essentially what you keep that is some kind of history table. And this is called the branch prediction buffer. And it indexed by the recent branch instruction addresses. And you store the outcome, whether it is taken or not taken. And in order to decide what to do when a branch appears, we look at the history table and we predict depending on what has happened before. We expect the same outcome, and depending on that, you start fetching, the pipeline start fetching the fall through, that means the next instruction or the target instruction, depending on this prediction outcome. And in case if it is wrong, then flush pipeline and you flip the prediction a bit. You flip the prediction status. Okay, so let me give you an example here. So this is we just keep track of just the immediate history. What happened to the last branch? This is called 1-bit predictor. So regarding the history of branches, you keep track of what happened in the last branch. Now in programs, this kind of structure is very common. You have these nested loops, right? So you have one loop, then another loop, and then another loop, and so on. And more interestingly, suppose that each loop is being executed 1,000 times, then what would happen to this inner loop? So it would be multiplied by 1,000, 1,000, and 1,000 so many times, right? Suppose I have 3 nested loops, and each of them should be executed 1,000 times. On the average, excluding the branch cases and so on. And this branch is this is the loop. This is the branch instruction which takes you to repeat this loop. So as you can see, this inner component, this inner portion of the program is being executed maybe 1,000,000 times. If there is a deep nested loops, right? So you are going to predict here what is going to happen in this branch. So that's why this prediction is very important. Okay, because this branch, this branch instruction, which corresponds to this inner loop, that would be executed multiple times, a large number of times. And if you need to pay a penalty for each of them, so that would be too much. And that's why this management of control hazard is more important. So suppose we assume that I have 1-bit predictor. I just keep track of, initially I set that branch not taken. And if the branch is taken in the runtime, then I will flip my prediction bit. I will flip my prediction status and I'll follow the prediction next time when that branch is encountered. So when this inner loop is being executed, okay, suppose my prediction bit, the first time the branch is taken and sometimes this branch is being taken. Okay. Now, at some point of time, you will make an exit from this inner loop, isn't so? And go into and reach the next loop. So therefore, there will be one misprediction on the last iteration of this loop. If you take this 1-bit predictor. And initially, if you assume that branch is not taken, so first time when you encountered this branch instruction, there will be a misprediction. So for every inner loop, there will be two misprediction, isn't so? Assume that initially you initialize your prediction to not taken. So first time when you are encountering this branch instruction, there will be misprediction because the branch is taken, and you flip the branch bit to taken. So keep on taking is all right, but when you are making an exit from here, then there will be another misprediction. So you would mispredict as taken on the last iteration of this inner loop, and it would mispredict as not taken on the first iteration of the inner loop next time around. Do you follow me? So here the situation is, the scenario is you have nested loops, and at the end of the loop, there are branch instructions. Now, when the loop is being iterated, the branch will be taken, and when you are making out of this loop, when the boundary condition is fulfilled, then you make an exit of this loop, and then the outer loop will be executed, and so on. So we are trying to see the behavior of the branch prediction for these loops, for this branch instruction. So if you have one bit history, like whatever happened in the last time during runtime, and I would follow that and initialize with branch not taken. So in the first iteration of the loop here, there will be misprediction because the branch is taken, but you predict not taken. And at the time of exit, you predict that it is taken because previously it was taken, but now it is not taken. So there will be two misprediction per loop, per inner loop. Is there any way you can predict this? I mean, can we improve the performance? By improving performance, we mean we want to improve the prediction accuracy. By prediction accuracy means the percentage, the fraction for which your prediction is correct. Suppose I predicted 100 times, where the branch outcome is being predicted 100 times, and out of that 90 times the prediction is correct, then the prediction accuracy is 90%. 10% prediction is not correct, and you need to incur stall for those instructions. So basically, prediction means you are keeping the history of the branch taken or not taken, and you want to follow the trend. What happened last time. Depending on that, you take an action. Now, one bit prediction is the simplest one because you need to keep only one bit per loop. We are assuming that there is only one branch instruction at the end of each loop. So if the bit is set to 0, it means that the branch is not taken. If it is 1, the branch is taken, something like that. Is there any way you can improve the prediction accuracy? In runtime. Can you extend this idea of one bit prediction to something else? Yes, no? Hmm? If you keep more history, then would that help? Any answer? Can you hear me?
Yes, sir.
What I'm saying that, so you are keeping in history here, what happened last time, and then making the prediction what would happen this time. And 1-bit prediction means I'm keeping just history of the what happened in the last time only. And as you can see that if you do that, for each loop, in a loop, there will be misprediction twice. Assuming that the loop is being executed a couple of times and then you exit from this loop, which is the typical behavior of a nested loop. If you keep additional history, if you keep a little bit more, if the depth of history is little higher, would that increase your prediction accuracy? Instead of 1-bit prediction, suppose you were observing what happened last time, but suppose you observe what happened last time and what happened just before that and so on. No, of course, if you keep the history in the, longer history, then you would have a little bit more prediction, a better prediction. So in this case, inner loop branches, like mispredicted twice. And in order to increase the prediction accuracy, you can increase the history, the depth of your history. So here you observe what happened last time, at the same time, the last but one time also. And you don't change the prediction bit as soon as the prediction is false. See here, I just forgot to mention one thing. Initially, you initialize your prediction to not taken, and when you observe that the prediction is actually, the loop is actually taken, then you swap the prediction bit, and follow that. And again, if you have a misprediction, you swap that bit. And in 2-bit prediction, and obviously this increases prediction accuracy because you keep track of the previous status and the last but one status as well. And here you change the prediction status on 2 successive misprediction. And this is the diagram for, this is the abstract, this is the, what should I say, that a financial machine for that takes care of, that represents the behavior of the 2-bit predictor. So this is the state which corresponds to the predict taken. Suppose you are in the predict taken stage. That means if a loop is encountered here, at this moment, I would predict that it would be taken and do appropriate action. Now, if the loop is actually taken, then the status does not change. Okay. Now, suppose you predict the loop is taken, but in real life it is not taken. So then you do not change the status. You still keep your status predict taken, and if there are 2 successive not taken, then you change your prediction not taken, and so on. So if you predict not taken, and if you have 2 successive taken, then the prediction status is changed. In other words, you are just keeping a deeper history, depending on what happened the last time and the last but one time, you make a decision. Now, even then, your prediction may or may not be false. I mean, may not be true, but it would reduce the falsity of prediction. Or would it increase the prediction accuracy at the cost of storing 2 bits per loop? Now, as I have said, that branch prediction is a very important topic in advanced architecture, and you would learn more about this if you take the follow-up course on high performance computing. Well, now let us move ahead. Even with prediction, you need to calculate the branch target anyway. And as we have seen that with hardware modification, still I need to pay 1 cycle penalty for a taken branch, even with prediction. Now, one way to reduce this penalty is to keep something like a branch cache, which holds the target address, so that we don't have to wait for the target address updation. So it's something like cache of target addresses. As soon as you're keeping on the loops, you don't need to compute the target address by the hardware. You can just pick up from the cache. Now, this is a separate cache, which is not the part of your main memory. It is specifically designed to hold the branch target addresses. So instead of computing, you can just fetch them from the target address if there is a heat, and if the predicted branch is taken, then you can fetch the target immediately without waiting for the address computation. Anyway, so these are minor kind of thing, minor modification by which you can improve the performance. So this is one thing. Maybe we can discuss one example here. Now, you remember that when we discussed data hazard, and an instruction just follows the load, and which is called the load used data hazard, that cannot be, and then one stall is inevitable. However, if there is an option for code reshuffling, I can put another instruction in between the load and the following instruction, then that stall can be compensated, just reshuffling the code. Similarly here, as you can see that in branch, even if you predict and even if you have those additional hardware for computing the branch address earlier in the pipeline, still you need to, one stall is inevitable, right? So similarly, between the branch and the following instruction, if you can put something else which will be executed anyway, but does not depend on the branch or the subsequent instruction, so then the slot where you are putting the stall, that can be reused by something else, by reshuffling the code. For example, here, if I have a branch, if S2 is 0, so some comparison is 0, then so this is my target here, and this is there is an instruction which is actually as I said, that even in the presence of the hardware and with prediction, you may have to incur one delay, right? Once one stall may be necessary if the branch is not taken, if the branch is taken. So what we do that, suppose there are some instruction which does not depend on this branch and so on, and it is somewhere here, you can bring it here, like this. So therefore, by the time this decision is being taken, whether the branch will be taken or not taken, during that time, this instruction, which is a sort of independent instruction, enters into the pipeline and can be executed. So therefore, the stall which you need to give in case the branch is taken, that can be reused by some other instruction. So overall, there will be no stall. So that is the idea by reshuffling the code. If this gap can be used to execute any other instruction, which may be determined by the compiler depending on the data flow. So then this delay slot can be properly utilized. You got it? Just like what you did in the case of load use data hazard by bringing some other instruction just after the load, similar thing here. And of course, here there are many other variations because the branch may be in the forward direction, it may be in the backward direction. And depending on that, so if the branch is in backward direction, the compiler would see that whether some instructions are here, which can be brought in the slot and so on. Let us not discuss that. I think you got the idea that the delay slot means that it is the place where just immediately follows the branch. And if the branch is taken, then the stall which is normally used, that slot can be used by some instruction which is not dependent on this branch instructions and so on. So reshuffling of code might help in order to utilize this slot. You follow me?
Yes, sir.
Yes,
Okay.
yes.
So I have explained the first case. You please go through these two cases. Similar ideas. Okay, so this is now our last topic, that how would I identify that the hazard has actually occurred? And if necessary, how do I enable stall and so on? And how do I enable the forwarding paths, and how do I enable stalls if needed? What kind of hardware modification or hardware resources we need in order to implement forwarding, and in order to recognize hazard, in order to implement forwarding, and in order to implement stalls if necessary. And as you see that we are determining this in runtime. So therefore, those decisions should be made depending on this register information. Whether the source register of something, say for example here, so there is a data hazard here, as you can see. The source register of AND is a destination register of the previous instruction and so on. Okay, so we need to recognize whether this kind of coincidence, that the source of this coincides with the destination of the previous one, we need to recognize that, right, in runtime. And one clear thing, that both the instructions, they have entered into the pipeline because they are sequential instruction. So the information about these registers, that's already in the pipeline. So the idea is we can, and this information are normally stored where? About these registers in the pipeline hardware layout. Where do I store this information about this source register, destination registers, and so on?
So at the interface latches.
Right, in the interface latches, and that information is copied to the next interface latch as the pipeline moves forward. We keep on copying those information from one stage of latch to the next stage when the pipeline moves forward. So in order to recognize whether or not an hazard has occurred, all I need to do is to tap those information from the interface latches and compare whether they are same or not. Whether the destination register is same as the source register of a following instruction and so on. So for example here, so this is the pipeline, the if IDR X mem WB. The next instruction, the next pipe just shifted by 1 clock pulse, and these hazards can be eliminated by enabling this. First of all, I need to recognize this, whether or not this hazard has occurred, and if so, then I have to enable the forwarding path, right? Because all the time I am not, regardless of this instruction, I am not going to enable the forwarding data path, but then it would be disastrous. The forwarding data path would be enabled only if this hazard is recognized. The need for passing this information to the next instruction is required. Well, so here, as you can see, that I need to recognize that this is indeed a data hazard, and I need to enable this forwarding data path. Right? In fact, in hardware terms, this is a backward data path, as we discussed earlier. That we need to enable. That means those multiplexers should be set in such a way so that this data from the output of this execute stage might be available to the input to this execute stage. So let us see how you can do that. We can resolve the hazard by forwarding, but the question is, how do we detect when to forward? Okay, so that is the basic question. What sort of hardware do you need so as to detect this the event of hazard, and how to enable this? Okay, so typically this forwarding is shown by this kind of data flow. But let us see that how do we recognize this. First of all, let us understand that in the pipeline machine, now as before, we have this control circuit which generates all kinds of control signals that enables the multiplexers and so on to set up the appropriate data paths in the. So this controller is almost the same in the case of single cycle implementation, but with little modification here. Now, since you have these pipeline stages or interface registers, the controller information is also passed through. So this is the different, the different portion of control signals you need here. Okay, as you cross the pipeline, so for example, this is the execute stage. And as we cross this, this information is no longer required, only these two portions will be required. Okay, so the control information is also passed through these latches step by step. Okay, so keeping this in mind, so these are the interstage pipelines, and the same information flows through the pipeline also as the pipeline moves forward. The question is how to detect when to forward. We know that these register numbers are passed along the pipeline latches, right? So we use this symbol. It means that you are in the interface between ID and EX stage. Okay, so this is the interface stage between following ID and before execute. And dot register RS means this is the ID of some source register. It means that when I say this this notation, it means that register number for the source register, each register has an ID, so that that ID value sitting in this pipeline interface latch in between ID and EX. Okay. Similarly, if it is between EX and MEM, we'd use appropriate lesion. Consider this code snippet. Okay, so here So this is the instruction which enters into the pipeline first, and this is the instruction which enters into the pipeline next. Okay, so what do I need to check? So whether these two registers are the same. So therefore, the destination register of this instruction, whether this is same as the source register of one of the, there are two source registers here. One is called S, and other is called T. So one of the source registers should, does it coincide with this? Okay. So what do I need to check? When do I recognize the data hazard? Can I say that if whatever, say, so now this is already entered the pipeline, and this is currently, suppose in this stage, execute is over, and the information is stored here in this interface latch. So in the interface latch between X and mem, okay, so X and mem dot register RD, that means the destination register currently saved in this interface latch here, whether this is equal to the source register which lies at the interface between ID and EX. If so, so then this register is the same as this one, isn't it? So all we need is a comparator. We need to access this information from here and also here from these two subsequent. These are two consecutive interface latches. This is the preceding one and this is the successor one. So we just take information. We just tap out the bits which corresponds to the ID of these registers and make a comparison. Do you follow the meaning of this legend?
Yes.
Is
Sir.
it okay?
Yes, sir.
Is this the only case, or there are other cases also?
There will be other cases for load.
Instead of T1, suppose this is T5, so then this register will match here. Even then there will be problem, right? So since there are two source registers here, so you have to check for both. So one is this, or XMEM register RD here is the same as IDEX register RT. These two of them are, one is called RS and one is called RT. So either this or this. And if so happens, then what you are going to do, you enable the forwarding hardware, the forwarding part from XMEM interface to the input to the ALU. So that means you enable this pipeline, this forwarding hardware between X and MEM to the execute stage. So this is the recognition part, and once you recognize this, that this comparator circuit generates a signal which controls this multiplexer. Well, now this may be a load instruction also. In that case, you may have to forward from here. So in that case, the condition would be mem/WB register, destination register is same as the source register at the IDEX stage. And since there are two registers here, for the other case also. So if so, so this will enable, this will recognize the need for forwarding, and the output of this comparator, if this comparison is true, that will enable the data path from memory to memory WB between this stage to the execute stage. So that is the basic idea. I think You got the idea how in hardware this is implemented. Now, one thing you have to make sure that see that the notion of destination register, source register, this is also there in the, suppose instead of add, this is a shift instruction. So the previous instruction has to be written all the time. Otherwise, there is no need of this forwarding or so, isn't so? And there are some special cases also. For example, this register may be $0 or something, then nothing is changing, nothing is being changed. So there are some exceptional cases, and for those cases, so if there is a further checkup, the previous one must be writing something. Either if it is a load instruction, it is going to write here, or it is this arithmetic instruction, it is going to write here. So this register write bit, which is the control bit, that should be 1. In order to safeguard this kind of forwarding operation, and make sure that the register destination is not $0 because that cannot be changed anyway. Anyway, these are small things for refinements only. But I think you got the idea how to recognize when to the need for forwarding and how the forwarding hardware is being executed. It should not be $0, so that means these are additional checks which are needed. Anyway, those are trivial examples. So here, as you can see, so this is the forwarding unit which recognizes whether and how to do this forwarding path. So these are, as you can see, the information from these latches, information about RS, RT, RD, and so on. So that is received by the forwarding unit from different latches. And then this forwarding unit takes the decision whether this multiplexing path has to be opened. So if you look into this path, if you look into this multiplexing path, this is coming from this latch. So if this multiplexer is enabled accordingly, so then data from this latch, from this stage of latch would be fed back to the ALU, and similarly from this stage. So the forwarding unit takes information from these latches regarding the source and destination registers, makes a comparison, and depending on the result of the comparison, it enables this multiplexer so that the appropriate data path is set. Of course, there are many other details inside the forwarding unit, but we may not have that much time to discuss all these details. Okay, so here is an example for you. So this is the load data hazard. I have a load instruction and followed by a subtract instruction. And so there is a clear hazard, and we need to make a stall here because it is being known here, and I want it here, right? So again, in order to recognize the hazard, I need to do the same thing, whether the source register coincides with the destination register of the previous load. And one stall is inevitable here because we need to make a gap between these two instructions. Okay, so we need to insert a stall. We need to first of all recognize that there is a hazard, and we need to insert a stall. So first of all, let us see that how do I recognize that there is such a hazard has occurred. Here stall is inevitable. We discussed that, right? So load use hazard is detected when do I detect that there will be a load hazard has occurred? What sort of register I need to check? Hmm? Which register do I need to check?
Sir, mem2 reg.
Hmm. First of all, we need to recognize that whether is load instruction. That means first of all, I need to know whether there is a memory read request, you know. So IDEX memory read should be, that line should be enabled, right? And IDEX register RT. Here, IDEX. Where is it? Yes, IDEX register RT is IFID register RS. We can recognize it beforehand here. You can see we don't need to wait for this time because these two, once you are here, the load and subtract, they have entered into the pipeline, right? So IDEX, it is a load instruction that IDEX memory read should be on here because that information will be passed here, and then when it reaches the memory would be enabled. You know? But it is already available as soon as this is entered into the pipeline. So IDEX memory read, I want to recognize it earlier in the pipeline because I need to insert the stall, you know. You understand why? So IDEX register RT should be IFID register RS. You can recognize here, right here, whether these two are load followed by another instruction which uses it. We want to recognize this event, occurrence of this event earlier. We are not waiting for here. Because all these informations are copied, you know, already here, and they are going to pass from one stage to another stage. So once these two are already read, you know, it is already read here, we know what is happening. You know. And there are two cases because there are two possible sources here. One is RS and one is RT. So similar. If this is so, then there is going to be a load hazard. You know. So now we need to insert a stall. Stall means what? Nothing will advance into the pipeline, you know, you just wait. I mean, no forwarding, I mean, nothing else would enter into the pipeline, but you let the previous instruction to advance so that this memory operation is completed. Do you understand the meaning of stall? When I say stall, it means what? You let the first instruction to advance. You don't let the remaining instruction to proceed through. Okay. So that means you need to stop advancing the pipeline for the successor instruction. And this can be implemented. So once it is detected earlier in the pipeline, if detected, you stall and insert bubble. You know. Now, let us see that how would I insert a stall? What I'm going to do that I'm going to force control values in this register to 0, you know, so that X, mem, and WB perform no operation for the successor instruction. So let me show the diagram, you'll see what is happening. And the used instruction is decoded again, following instruction would be fetched again. Stall means whatever is entered into the pipeline is flushed and after one clock cycle, this is refetched and re-executed. And one cycle stall is here needed anyway when a load followed by an R type instruction. Okay, let us look at the diagram. You'll see how it is being happening. So this is the hazard detection unit. As soon as the hazard is detected, that means this when that Boolean condition is true, which we had just shown in the previous slide. So then this controls a multiplexer, and so and all this pipeline stages, they are frozen with 0, so that the successor instructions, they cannot proceed through the pipeline. You just let the previous instruction complete it, and you know that how many, the one clock cycle should be needed, and after that you refetch the previous subsequent instruction and proceed. So that is being controlled by this hazard detection unit. How to freeze this. So this is the forwarding unit for enabling the data path. This is the detection unit for enabling hazards as well as to implement stalling. So I have tried to give an overall idea that how this can be implemented. Of course, there are lot of hardware details behind it, which is beyond the scope of our discussion. So that finishes our major topics in the pipeline management as far as this course is concerned. So we talked about 3 different kinds of hazards and the impact of hazard on the pipeline flow, the techniques of forwarding, the techniques of hazard detection, and stall insertion, and so. So basically, as you see that when you are forced to include stalls in the pipeline, that reduces pipeline performance because it's being slowed down. So ideally, at every clock cycle, one instruction should be completed. But now, because of stall, that the progress of the pipeline is slowed down. And we have also seen that in both for data hazard and control hazard, the compiler may play a major role in reshuffling the code so that whenever the stalls are inevitable, so those slots, if can be filled with some other instruction, so then the overall performance would increase. So instead of inserting those stalls, we can use the stall slots to execute some other instruction, therefore not impacting the overall performance. And of course, the compiler should be aware of the pipeline structure. Otherwise, how would you reshuffle the code and so on? So you need a very smart compiler for if the target machine is a pipeline machine. So now this is the last equation that we'll be discussing in this course. It is the performance equation for the pipeline machine. We want to see that in the presence of stall, how the performance would degrade. So first of all, let us talk about pipeline speed up in an ideal machine. Assume that is an ideal scenario and no stall. My pipeline is fully balanced. So the maximum speed up is that you already know. So can I write this way? Now, when I say speed up, it is speed up in comparison with an unpipelined machine. Can I say that is the number of clock cycle per instruction for the unpipelined machine? average number of clock cycle per instruction for the unpipelined machine divided by the average number of clock cycles in the pipeline machine. Agreed? And this would be the same as, in terms of CPU time, this will be the CPU time in the unpipelined machine and divided by the CPU time in the pipeline machine. So what is the value of the CPI for the unpipelined machine? The first term.
Five times.
Yes, pipeline depth, right? Pipeline depth, to be more particular. And what is the CPI of pipeline in ideal machine?
So one.
One. Once the pipeline is full, then one. Okay, right. So this is pipeline depth divided by CPI pipeline. Ideal CPI pipeline is one. Once the pipeline becomes full, and if the number of instructions are too many, I mean there are a large number of instructions to follow, so then the CPI value would tend to 1. So therefore, this is approximately equal to pipeline depth. That we have already know. And there are some pipeline overhead in the sense that because you have interface latches and a lot of hardware, etc., that inserts some delay. So therefore, in the non-ideal case, I mean, forgetting about this hazards and so on, in the presence of this additional overhead, hardware overhead and so on, this we have a little value which is not exact pipeline depth, but less than that. So now in the presence of stall, what would happen? So you have a program and you have run that program on the pipeline machine, and we have several instructions, and at the end maybe we have say 100 stalls. Several data stalls, I mean stalls for data hazards, stalls for control hazards, and so on. Total number of stalls, something. But we are going to compute in terms of the average number of stalls and per instructions and so on. So pipeline speed up in the presence of stalls. As before, we can write the same thing, right? CPI for unpipelined, average number of clock cycle per instruction for the unpipelined machine, divided by the CPI for the pipeline machine, but the realistic machine in the presence of stalls. So in the ideal pipeline, the CPI is 1. In case of stalls, what would happen the CPI of pipeline?
It would increase.
That would increase. By how much amount? Now the numerator is pipeline depth as before. The denominator is, in the ideal case, it is 1. You rightly said it would increase, but by how much amount? This is the average number of pipeline stall cycles per instruction, right? Because we're talking about this average value of clock lines, average value of clock signals per instruction here. So this is an incremental sort of stuff. Averaged over total number of stalls divided by divided by the number of instructions in the program. There's the average number of pipeline stalls per instruction. That would impact the average. So this 1 plus this fraction, right? Or whatever. So therefore, as you can see that in the presence of stall, this speed up reduces from the ideal value. So just for an example, that suppose we want to evaluate what is the pipeline speed up in the presence of branches. Assume that you can assume that, well, I have a very big program and suppose the number of branches, the branch percentage is something, the branch frequency is something, and you know the branch penalty, you know, it may be 3, it may be 1, depending on what kind of architecture you have. So given that, can I write this way that pipeline speed up that takes care of this branch penalty is given by pipeline depth 1 divided by 1 plus this average number of pipeline stalls per instruction. So that would be in case of branch. If I know the branch frequency, there's so many fractions of, I mean, say for example, 30% of my instruction, they are branch instructions, divided by, assume that this is the branch penalty, you know. For my implementation, suppose my branch penalty is 1 or whatever. So then I can estimate this my pipeline speed up in the presence of stalls. And similarly, you have similar expression for data stalls and so on for data hazards. And if you know the total number of stalls, including both data hazard and control hazard, you can use this relationship, right? So that's how you can estimate your speed up. Okay, very simple expression. Follows from the first principles. All right. So you remember in the beginning of the course, we started with our famous CPU performance equation that CPU time is CPI times IC times CPI times CCT. And we finished our course using just this modified performance equation that tells about the speed up, which relates the pipeline depth and the average number of stall cycles per instruction. So in summary, one of the main topic in the context of pipelining is the study of hazards. So these are situations that prevent starting the next instruction in the next cycle and which slows down the pipeline. And effectively the value of CPI increases and the pipeline decreasing the pipeline speed up, you know, from its ideal value, which is its maximum value is the pipeline depth. And we know that there are structural hazards, a resource is busy. And in order to avoid structural hazards, we need to insert bubbles or separate instruction data memories or caches. And in some other advanced architecture, you may need to do appropriate action. You may need to take appropriate actions. There's a data hazard. Then you need to wait for the previous instruction to complete its data read or write. And we have studied various techniques that use bubbles or stalls, use half cycle strategy for register write in the first half cycle, register read in the second half cycle, data forwarding from different interface stages to the input of the ALU and so on, code reordering by compiler. We have also studied that how these hazards can be detected, how the forwarding data paths can be enabled, how the stalls can be enabled whenever needed. And finally, control hazard, deciding on the control action we have just discussed today, how to manage that by modifying hardware and by reshuffling the code, which is called the management of delay slot. And so these are the typically 3 major hazards we encountered in pipeline. More details you will study in your advanced architecture course next time. So in summary, pipeline improves the performance by increasing the instruction throughput per cycle. And it executes multiple instructions in parallel because the several modules of the hardware, several hardware resources or modules, all of them become busy in processing the instructions, in processing several instructions simultaneously. But the latency is not increased because completion of each instruction takes the same time, but the rate at which the instructions are finished, that is improved. They are subject to different kinds of hazards. And of course, as you can see that the entire pipeline design is based on our instruction set or ISA architecture. And we have restricted our discussion is restricted to the MIPS architecture, which is based on the 5-stage pipeline. And therefore it strongly influences the it is strongly influenced by the instruction set design. In concluding remarks, as you can see that the overall instruction set architecture influences the design of data path and control in the pipeline structure. And conversely, which is no so apparent, that this data path and control influence the design of ISA as well. Because you have hardware limitations and so on. So, you cannot have a random sort of ISA. In that case, it may not be physically implementable, so easily implementable. So it is both ways. ISA influences the pipeline architecture, and at the same time, there are hardware limitations on data paths and controller, which influence the design of instruction set architecture. So it is basically one step forward to parallelism. Later on, this will lead to superscalar architecture and so on. So more instruction completed per second, latency not reduced, structure different kinds of hazards, dependencies, and those limit to achieve parallelism and so on. And there is a limit on the power wall also, because as the hardware layout, hardware layout increases and the complexity increases, more and more power will be consumed, but there are limitations on that. So you may hit the power wall. That means, you cannot increase all kinds of hardware complexity in a chip, because a huge amount of power will be dissipated and chip would become very hot. And so therefore there is a restriction on the maximum power the chip can withdraw at any instant of time. So this is called power wall, which limits the hardware complexities. Handling exceptions, like when exceptions occurs that disturbs the pipeline, and handling exceptions, they need separate discussion. And there is a lot of research has been done in handling exceptions in a pipeline machine, like interrupts and so on. And that is taken care of in the advanced architecture course. So with this, we finish our discussion, and this is the last class of this semester. Now, so the entire semester has become online, so it's bad that I did not get any opportunity to meet you in person or see you. Maybe when the things will be normalized, please drop by sometime in my office so that at least we can recognize each other, Well, so that's all. We are done. This is the last theory class. Thank you very much for having been present in my class. Any question? Or any comment?